Alright folks, wanted to post this up and walk you through our screening and the example of the repeated measures T, but just as a quick refresher before we jump right into things, remember that with our repeated measures designs, what we're doing is we'll have the same group of individuals and we're evaluating them at multiple time points, right? In our very basic, most simple design, we're talking about a paired sample t-test where we've got two measures, time 1 and time 2, and what we're looking at is to look at change within individuals across those repeated measures. And so the thing to remember about our repeated measures design is our primary unit of analysis here is a difference score. All right, T1 minus T2, we're going to get a difference score, and the mean of our difference scores is going to be the data that we're working with the paired sample T. So if you can remember that, that will be helpful in trying to keep all this stuff clear. So remember the null hypothesis: if the difference scores are our unit of analysis, null hypothesis is that the mean of different scores in the population is equal to 0. Our alternative hypothesis is the mean of the different scores is not 0 in our non-directional hypotheses. The design, looking at what is the mean of the different scores in the population, we don't know. We're going to get a sample, take a look at the sample and see if, based on the data that we're observing here, whether or not we have sufficient evidence to claim that the difference score in the population is some value that's different than 0. And again, the question, do different scores across multiple assessments deviate sufficiently from 0 to conclude a non-zero difference in the population? Our paired sample data, calculation of our t-statistic, we're taking the mean, our observed mean of our different scores, and where'd my cursor go? Mean of the different scores, and subtracting our assumed mean under the null, which is 0. That goes away. So we've got our mean difference score over our standard error of the mean difference. Standard error is going to be the standard deviation of the different scores divided by the square root of n. So in this small set that we can see here, we've got participants A, B, C, and D, scores at time 1, scores at time 2. These different scores is going to be what we're going to actually analyze when we're calculating our paired sample t-test. We've calculated our differences here, calculated the mean of the difference score, the standard deviation of the difference score, and this is what we're going to use to go through and calculate our test statistics there. Again, question that we're looking at, what's the probability of obtaining a set of different scores with mean of 3.5, assuming the null hypothesis is true, assuming that in the population the mean of the different scores is actually 0. Okay, this should look familiar. Again, as we talked about in lecture, this formula is just the basic, the same formula we use for a single sample T, because we just have one sample here. We're just looking at this column of different scores in the calculation of this. If you remember, t-statistic for our single sample T, we're taking our observed mean minus some population reference value over the standard error. Standard error is our standard deviation from our sample over the square root of our sample size. Same thing going on with our paired sample test. The only thing that's going on is our unit of observation here is our difference score. Okay, so formal assumptions of our paired sample t-test. Our outcome is continuous. Okay, again, we fudge on this a little bit, and sometimes we'll often use our ordinal scales that technically are our Likert type scales that technically aren't continuous, but if we've got a Likert scale with 5 values or more, we generally are okay saying treating that as though it's continuous. And then our other assumption, that we're assuming that the sampling distribution of our difference scores in the population is normal. Okay, so again, the sampling distribution we're worried about with a paired sample T, less concerned with our observed the distribution of our observed scores, although we'll want to take a look at that. The real assumption here is that the distribution of different scores in the population is, or the sampling distribution of different scores in the population is normal. So again, remember that our sampling distribution is going to very quickly become normal if one, either the scores from which the population, or the population for which the scores were drawn has a normal distribution, or as our sample size starts to increase. Even if the distribution of scores in the population is wildly non-normal, as soon as we start to get larger and larger sample sizes, it starts to address that. So again, in terms of samples, generally bigger is better. Okay, informal assumptions that our data don't contain any outliers, and so we'll want to go through and take a look at that when we're doing our screening. Okay. Effect sizes, again, talked about. The big thing here is questions about what you want to use as your standardizer. What's the unit by which you want to calculate or use as your reference to take a look at units of standard deviation change? Mean difference score. That's a very simple and straightforward measure of effect. Great if we have outcome variables that have intrinsic meaning. A lot of times in psychology we don't. If we're using years of life, money, things along those lines, then I can say, oh, the difference between in income before education and after education is $20,000 or $10,000 or something like that. That means something. Or the difference in time spent working through something before training and after is an hour. So those are the types of things that make sense and can be useful in terms of just looking at the mean difference. However, for a lot of things that we do, we're using arbitrary scales, measures where the units don't actually mean anything intrinsically, and so this is when we're looking at our standardized measures of effect. Here, bring this up. This is our basic formula for Cohen's d. We've got the mean of the difference over the standard deviation. Well, fine, but the question is, which standard deviation do we use? We have a couple of different options. So Cohen's here is sort of our base, but in actual practice, when we're sort of actually calculating, we have to decide what we want to use as our standardizer. So we can use the square root of the average variances as our standardizer. You think about this as similar to what we were using with our like Hedges G, where we're using a pooled variance estimate as our standardizer, or the square root, taking the standard deviation of our pooled variance estimate. Here, because it's a paired sample test, you have the same number of people throughout the thing. So if we start with 10 scores, we'll end with 10 scores. If we don't get a second assessment on somebody, they're not going to be in the analyses. And so what we can do is we can take the average of the variance at time 1 and time 2, and take that average variance and then go through and take the square root of that to get our standardizer. Okay, this is often a good approach if you just want to take a look at standardize your effect in terms of the average variance across both of your time points. Okay, other option is Glass's delta. Just like we calculated this from our independent sample t-test, this is a nice approach if you have some sort of meaningful baseline. Basically here, what you're doing is standardizing your scores based on the variability or the standard deviation when people are coming in. So if I have a weight loss program, so I bring people in and I take a look at the variability of their weight when they come in, and then we go through, have them complete the program, measure their weight after. Here we get the mean of the difference in terms of weight at pre-treatment and at post-treatment. But then what we're going to do with Glass's delta is use the standard deviation of scores when people came in as our standardizer. Again, this is nice because it provides a nice interpretation, and you're talking about units of change or standard deviation units relative to the normal variability that we would have in the population before we did whatever we were going to do in terms of our manipulation, our treatment, or things. Last thing we have here is an R squared. This is for secondary analyses. If someone gives you a t statistic, you can square the t and take that over the sum of the squared t statistic plus the degrees of freedom. This gives you an R squared effect, which is a metric that is sometimes used in aggregates, like meta-analyses and things along those lines. We can calculate this, but it loses some of its intrinsic meaning to some extent, given that we're using a means-based analysis. And so, just an FYI, you can use this, but in general, we'll probably want to use some version of Cohen's d. Okay. Other thing that we have, remember, we can calculate d using the standard deviation of the difference scores as our effect. Now, remember, we talked about this as the concern being oftentimes you'll have larger variability at time 1 and at time 2 than you will in terms of the standard deviation of your difference scores. So, for example, if we're doing something with like physiological data, like skin conductance, different people sweat differently across, there's a lot of individual differences in terms of if I were to just hook you up to our physiological equipment and measure your skin conductance, some of you would have very low skin conductance, some of you might have very high skin conductance. We'd have a lot of variability both at time 1 and time 2 just based on individual differences, right? And so if we looked at the variability of skin conductance scores at time 1 and time 2, there'd be a lot of differences, a lot of error around the mean there, right? But what's probably the case is if I hook you up, measure you at time 1, and then I do something, show you some affective stimuli or something like that, and measure you again, you might all change very similarly in response to that. If I have a good affective manipulation, doesn't matter where you start out, people may respond to it in a very similar type of way. And so we might see that even though we have great variability at time 1 in the terms of the scores and great variability at time 2 in terms of the scores, variability around our different scores might be pretty small if everybody's responding to it pretty similarly, right? And so what happens is if I calculate my effect size based on the average variance at time 1 and time 2, and then take the square root of that to get an average standard deviation, that might be a lot larger than the standard deviation of the difference. And what happens is, because this is a larger number going in the denominator, my d statistic that I calculate here is going to be systematically smaller than if I have much less variability in the standard deviation of my difference scores. So concern is that this formula may overestimate your effect. Other thing that's difficult with this, here we can talk about this in terms of change in standard deviation units of variability based at time 1 and time 2. That kind of has a little bit more intrinsic meaning than making this as an interpretation of this is standard deviation units of change relative to standard deviation of change. We get a little bit more of a difficulty with a practical interpretation with this. Now, the benefits of using this formula is that we can calculate a confidence interval around this. So if I want to use my paired sample t-test, I can run a test and I can make a determination on whether or not we have evidence of reliable change, and then I can calculate an effect size around that. And if I'm using this formula here, I can also calculate a confidence interval around that effect size, because the standardizer, the variance estimate that I'm using here in my denominator, is the same variance estimate that's going into the calculation of my t-statistic. And because, as we'll see, calculation of confidence intervals around effect sizes require us to use our test statistic in order to get those intervals, we want to make sure that if we're calculating a confidence interval around an effect size, whatever effect size that we calculate should be using the same metric of variability as that went into our test statistic. Okay? And then we have this last d paired. This is taking your Cohen's d that you calculated here, putting that up here, and then dividing it by a correction factor that takes into account the correlation between time 1 and time 2 scores. this starts to become relevant for calculation of power for our within subjects tests, but I would not recommend that you use this for your standard metric of effect when you're calculating your t-tests and things. One, it's going to be it'll be largely inflated relative to some of these other metrics, and then two, I don't know how we provide a practical interpretation on that. Okay, so small, medium, and large standardized benchmarks for our effect sizes here, and then small, medium, and large effects for our correlations if we wanted to take a look. The one thing to keep in mind, and I mentioned this in lecture, so we've got some asterisks here. Remember that the square root, or excuse me, the average variance in a paired sample test is going to be equal to your pooled variance. The thing that you want to be careful is that if you're going to calculate this, what you want to do is you want to average the variances first and then take the standard deviation. Okay, the standard deviation of your average variances is not going to be the same value as this average of your standard deviations. Okay, so again, what we want to do is we want to calculate our variance at time 1, variance at time 2, take the average of that, and then take the square root, as opposed to from your SPSS output, taking the standard deviation at time 1, standard deviation at time 2, and taking the average of that. That's going to be an incorrect value. We don't want to do this. This is what we want, not that, in terms of standardizing our effects. Hopefully you didn't see any of that. I'm hoping I'm able to edit some of that stuff out. But, so what we're going to do now that we're up to speed with our tests, how we're calculating it, and then our assumptions and effect sizes, things like that, I want to jump into the SPSS example of how to go through and do these. So what I want you to do is make sure that you have your handout here, your paired sample T screening, and your paired sample T test. So let's go over to the screening first. Okay. So what we have here, the data that we're going to be using is looking at treatment outcome in a small sample of individuals, and what we're looking at is change in a couple different measures of interpersonal style. Our first interpersonal style is this cold, distant style. So people's tendency to be sort of distant and aloof, which can be problematic. By contrast, our second measure is a measure of self-sacrificing style. This is being a martyr, putting other people's needs before your own, but too much so that maybe you have problems being assertive or other people take advantage of you, things along those lines. So the range for these scores, we have cold distant style measured at baseline, and then cold distant style measured at post-treatment. And then we have self-sacrificing style at baseline and self-sacrificing style at post-treatment. Okay, so if you have this out, what we're going to do is, is take a look at our data set here. Okay, so the first thing that we're going to do is we want to, for the purpose of the screening, remember that we have pre-post values, but that's not actually what we're interested in terms of looking at with respect to our screening. What we want to take a look at is, remember, we're evaluating the distribution and characteristics of the different scores. So what I'm going to do is I'm going to go up to Analyze, then Transform. So select Transform and then hit Compute Variable. Select Compute Variable, and what I'm going to do is I'm going to create a new variable. Then I'm going to call it dist_diff. Okay, and this is going to be my variable for change in this cold distant personality style. And what I'm going to do is I'm going to take my post-treatment score and subtract it from my baseline score. Okay, as you're going through, and it doesn't really matter, it doesn't matter which way you calculate this, one way or the other, but the nice thing is if you take the time 2 score and subtract it from the time 1 score, what you're going to get is a different score where the sign in front of it, whether it's positive or negative, is going to tell you the difference in change. So here, if we get a negative score, we know that we've seen reductions in cold and distant interpersonal style. If we have a positive difference score, that's going to mean that we saw increases in this. Okay, so named my variable, told SPSS how I want it to calculate, and then I'm going to paste this into my syntax file here. I don't like that. I'm going to get rid of that. But what I can do is I can now go back through the menu and calculate a different score for my self-sacrificing, but it's going to be easier for me to just go through and create it here. So I'm going to go sac difference, right? And it's going to be sac post, sac base, and there we go. And I've got calculation of both of my different scores, and I can go through and then label this and say calculating difference scores for screening or something like that, just to give yourself a reminder. Again, remember that anything that you preface with an asterisk won't be read as a command in SPSS. So what I can do now is highlight, just to show you, highlight the whole thing, go through and run. It's always nice to take a look at your output here to make sure we didn't get any errors or anything like that. So it's just telling us what commands we ran. Then if we go to our data set, we can see that we've calculated different scores for cold distance and self-sacrificing. Okay, and if we go through and take a look here, right, looks like all of we're not missing any values, and so we're excited about that. If we go through and look at our actual observed scores, again, we're expecting scores to range from 0 to 16, 0 being very low on cold distant interpersonal style, high scores meaning more severe cold distant style. But if we go through and take a look at all of these, all of our values are falling within the range that we would expect. Okay, so nothing missing. Our range of values is all reasonable given our scale, and so we're looking pretty good there. Okay, so we've gone through, calculated the different scores. What we want to do now is we want to go through and we want to take a look at the distribution of our different scores here. Again, we want to look for outliers, skew, kurtosis, things along those lines. So what we're going to do is we're going to analyze descriptive statistics, descriptives, and what we're going to do is we're going to take a look at our different scores, right? Because these different scores are a unit of analyses for our paired sample t-test. We'll go to options, skew, kurtosis, and then we'll click this so we get z-scores for all of our participants, and then we'll go ahead and paste that into our syntax file. Okay? And so you can then run this. You should get the same output on your handout, but we're going through and saying, okay, 19 people on our sample, we're getting 19 different scores, so everything sums up. Our minimum and maximum, right? So for cold distant behavior, we see our maximum reduction is a 6-point reduction, anywhere up to a 3-point increase. For our self-sacrificing score, 4-point reduction to a 4-point increase across the sample. Okay. Here is our the mean of our different scores, right? This is what's going to go into our numerator of our test statistic. This is what we're trying to determine whether or not we have enough evidence to claim a reliable difference from our assumed population difference of 0. Here's our standard deviation, right? And when we look at our skew kurtosis values, it doesn't look like it's too bad. We don't have a huge sample here, and so our graphs probably aren't going to look great, but looks like for difference in self-sacrificing scores, a little bit of positive kurtosis, probably not anything we'd be too concerned about right now. But again, remember, this is going to be a leptokurtic distribution, so it's going to be probably a little bit more peaked. Okay, but looking at our basic skew and kurtosis and indices, not seeing anything that we're too concerned about with that. Okay, so what we're going to do now is we're going to go up to Analyze, because what we want to do is we want to take a look at histograms, box plots, and things. What we're going to do this time is go to Descriptive Statistics, and then go down and select Explore. Okay, and what we're going to do is we're going to take our different scores, drop those into our dependent list. Okay, and then what we can do is we can take our research ID, it's our subject number here, and drop it into our label cases by. That way, if we have any weird values on our box and whisker plots, it's just going to attach their participant ID to that number as a set of the number at which their case number, depending on how we've got that data set sorted. So this will just attach their ID number to any outlying values, things along those lines. If we go to Plots, select Histogram, and then turn off stem and leaf. I don't like the stem and leaf as much, but I do like to have a histogram with this. And then go ahead and hit OK, and that should get us set up. Okay, so we're going to go ahead and hit Paste. So we can see, so this is our command here. We've got examine, so these are our variables. This is our stuff, so we can go through, highlight this, and run this. And so we get a bunch of different stuff with this Explore command. We'll go through, take a look and see if we have any missing values. We don't. Then if you go through and you take a look, we've got all the stuff that we had up here, right? It's provided from us down here. I just like this. This is easy for me to read as opposed to going down through. But with the Explore, we get a lot of other things too. We get the mean, our 95% confidence interval around our mean. We've got our standard error. We've got a trimmed mean. We won't worry about that. But then we've got our median value, our variance, standard deviation, min, max, range, interquartile, skew, kurtosis. So a lot of different potentially interesting information that we have here. So this is for our cold distant scores. Same thing for our self-sacrificing scores. But what really nice is that we get histograms and box plots for each. So this is our distribution of our different scores for cold distant behavior. Everything's looking pretty good. I mean, given this, that we have a sample size of less than 20, we've got one person that's a little bit disconnected from the overall distribution, but not too concerned about it. Box and whisker plot, nothing much going on here, right? We've got our median, we've got our first quartile, our third quartile, and then the value, our difference score that is sort of the farthest within 1.5 times the interquartile range. But everything's looking there. Our self-sacrificing score, remember we had gotten a positive kurtotic value of like 1.5, and we can see how it's kind of peaked and then has some flat tails coming out to the side. Again, we've got a gap in our distribution, but it's not huge. We're not too worried about it. So this is looking all right, again, particularly for a sample of 19. As we go down through and take a look at our box and whisker plot, again, median, first quartile, third quartile, the farthest value or the lowest value within 1.5 times the interquartile range, and here is our most extreme value within 1.5 times the interquartile range. But then we've got one value that falls outside of that. We see that after treatment, we've got one person who had a 4-point increase in their self-sacrificing interpersonal style. So we're seeing a big increase there. And this specifically is case number 2478. Okay, and if we go and take a look at our difference scores for self-sacrificing, if we sort that, we can see it's this one score, 2478, having the largest value in this distribution. Okay, so if we go back through and take a look at our output, so this is an extreme value, at least within by definition of the box plot, in that it's a value that falls more than 1.5 times the inner quartile range away from your third quartile. But in the grand scheme of things, if we go up through and take a look, it's this person right here. It doesn't look like it's going to be too much of a problem. So in your screening, we want to go through, take a look, make some descriptions or provide a description and interpretation of your histograms and box plots. But for this stuff right now, it's looking pretty good. Okay. Finally, what we want to do is go through and take a look at our z-scores to see if we've got any evidence of possible extreme values or univariate outliers. So if we go to descriptive statistics, we go to descriptives, get rid of those, and ask to take a look at our z-scores, right? And options, we can take off skew kurtosis because we don't need skew and kurtosis because we already know that. We don't need to have z-scores on our z-scores. I'm going to paste this in, okay? And here's our command in our syntax file. Run this, and what we've got there is our minimum and maximum in terms of our z-scores. Now this is a small data set, right? We've only got 19 people. I can just go through and sort of sort that. I can see, all right, that looks all right. Here's my lowest z-score, so I've got someone who's about 1 3/4 of a standard deviation below the mean, getting close to 2 standard deviations above, right? You do the same thing here. So about 1 3/4 of standard deviation below to about 2.5 standard deviations above. So with a small set, we can just take a look at it, but it's as your sets start to get larger, it's nice to have this here so you can just take a look at your minimum and your maximum z-scores. So here we have someone, and again it's going to be this person right here, 2478, who's registering a z-score of about 2.5, but given the distribution, everything else considered, the fact we have a small sample, I'm assuming that this is a member of our population of interest. Sometimes treatment's not going to work well for everything. Sometimes people might actually get worse. We don't have a lot of people to be throwing out. I don't think this score is going to be a huge influence on the mean, and so I think we're doing pretty good in terms of our screening on this. So, but would maybe note it that you got one value that's falling beyond 1.5 times the inner quartile range, that it's associated with a z-score of about 2.5, but given the overall distribution and that it's not separated far out from the rest of the from any of the, or the next largest case, I think we'll go ahead and keep that in. So overall, our data are looking pretty good. I think we've got reasonable assumptions here. I think we have no concerns over the distribution of sample means for different scores. We don't have strong evidence of clear, meaningful outliers here, so I think we're doing pretty good with our assumptions. Okay, so what we want to do now, and if you go through and you grab your paired sample T handout and take a look at that, what we're going to do after we've spent lots and lots of time screening, we're going to run our statistical tests, and that's going to take like 2 seconds. So you're going to go back to our data set. We're going to hit Analyze, Compare Means, down to Paired Sample T. Okay, and what we're going to do is first we'll look at our cold distant variable. So go through, and so when we use these arrows, it puts our cold distant at time 2, cold and distant at time 1, self-sacrificing at time 2, self-sacrificing at time 1, and so we're just setting up our pairs here. Options, You can change the confidence interval that you want. Right now the default is 95, which will probably be fine, but you could set that to 90, 99 if you wanted. And so let's go through and hit paste. Go through and take a look. Here is your syntax command for your paired sample. So we've got post, baseline, and this is just how SPSS is mapping this on. So first one here will be paired with first one there, first one here, first one there. Got that all set up. So we're going to take this, highlight it, run it, and this is our output. So we get up here in our descriptive statistics here, we've got the mean of our cold and distant scores at post-treatment, the standard deviation and standard error. We have our cold and distant scores at baseline. Here's the mean, number of observations, standard deviation, same thing. Our self-sacrificing scores at post-treatment, and the standard deviation, self-sacrificing scores at baseline and post-treatment. Okay. Here, SPSS provides a measure of the correlation between scores at time 1 and time 2. So we've got a correlation of 0.78 for our cold distance scores at time 1 and time 2, and a correlation of 0.9 for our self-sacrificing at time 1 and time 2. So very strongly related. Oftentimes we'll see this. But this correlation is what gives us the power of these paired sample tests. If scores at time 1 were unrelated to scores at time 2, our power reduces to what we would have in a single sample test. So for our purposes, this high correlation is encouraging in some respects, because it suggests that we're going to have the power to detect some really subtle effects over the course of these two measures. So moving down here, we see the mean of our difference scores. So this is the mean of the difference scores for our cold and distant measure, mean of the difference scores for our self-sacrificing. If you go back through and compare these two with the means that you calculated above, right, they should be the same, right? All SPSS is doing what you did by hand up here. They're just providing it down here. Same thing. Here's the standard deviation of the different scores, standard deviation of the different scores for self-sacrificing. If you go back up to the top of your file, same thing that we calculated in our initial screening when we were looking at the means, standard deviation of different scores. Okay. As we go farther down here, we have a confidence interval around our difference, right? So, or here's the standard error of the mean of our difference scores. Now, if we took this and divided by this, we would get our t-statistic here, right? So you can literally do this. If I take 1.684, I've got my calculator, 1.684, and I divide it by 0.567, and I divide those things, I get 2.9700, right? So within rounding error, we can see that going on. Actually, I don't know if you guys know about this, but if you double click on this, get that, it goes through and it calculates this sort of out farther. So a little trick if you want to go through and be able to like copy paste scores, things along those, you can get that out of your output file. But again, if you think back to your the calculation of your t-statistic, it's your mean difference over the standard error of your mean, right? And so if you take that and divide it by that, you're going to get your t-statistic here, right? Same thing, divide 0.684 by 0.433, that's going to get your t-statistic here. Your standard error of the mean, this is just the standard deviation of your difference scores divided by the square root of 19. If you take this, divided by the square root of 19, you're going to get your standard error of the mean. Just interesting to see how all this stuff fits together and maps onto the formulas that we've been talking about in lecture. So our 95% confidence interval of our difference scores. So for our cold distant, our cold and change in our cold and distant interpersonal style, we see that plausible values for the population range anywhere from about a almost a 3-point reduction in scores pre to post treatment to about a half a point reduction. We see that this doesn't contain zero, so we already know that this is going to be statistically reliable. Now if we go down to our change in our self-sacrificing, we range of plausible values anywhere lower limit of say a 1.5 point reduction to about a 1/4 point increase. We know that because that contains zero, before we even have to look at the rest of the test, we know what our hypotheses tests are going to tell us. But wanting to make a strong interpretation of our confidence intervals here. We move down, we see our t-tests, degrees of freedom, and our p-values for our two-tailed test. So it appears as though we have evidence for a reliable effect or a reliable difference or reduction in cold, distant interpersonal styles of pre to post, but really don't have much evidence of change for a shift in this self-sacrificing interpersonal style. Okay, so that's quick and easy. All we need to do to get our to calculate our paired sample tests here. Last thing that we would want to do is calculate some effect sizes. Okay, and so we have a couple of different options here. One, we could, because we have a meaningful baseline, right? So this is where people are coming in for treatment, where they start out when they first come in through the door. So our glasses delta might be an interesting effect size metric to calculate. Here we would just take 1.684, which is our mean difference, and divide it by our standardizer. Here for glasses delta, our standardizer is going to be the variability that's occurring when people come in at baseline. Oops, that's post. But if we take 1.684 divided by variability at baseline, 3.649, we're going to get an effect size of about 0.46. Okay, so we would interpret that as saying our effect size suggests about a half a standard deviation decrease in cold distance scores from pre to post treatment, which is sort of meaningful and getting close to our cut point or a benchmark for a medium effect. Or another thing that we could do, and I think glasses delta makes a lot of sense given sort of the setup of our question, but we could calculate this an effect size using the average of the variances as our standardizer, and then getting a standard deviation estimate from there. What we would do is, again, we would take the mean of our difference scores, 1.684, and divide that by the average of our variances. And so what we would need to do is we would need to take 3.649 and square that, right? And then we would need to add the square of 3.717, take those two variance estimates, add them together, and then take the average of the variances. And so your average variance in this case is going to be 13.555, right? But that's the variance. What we need for our standardizer is a standard deviation estimate. And so then what we would do is we would take the square root of that average variance, would give us 3.682. Okay? And so if we take 1.684 divided by the square of our average, or the square root of our average variances, which is going to be 3.682, and calculate our effect size as a D average, we're going to get an effect size again of 0.46. So in this case, your glasses delta is very similar to your D average, mostly because our variances here are our standard deviations here, and our variances as a consequence are going to be very similar. All right. Last thing we could do is we could say, well, I want to calculate this using the standard deviation of the difference scores as my standardizer. If I wanted to calculate a confidence interval around my effect size, this is how I would want to do it, right? And so if we're doing this, we're going to take our mean of the difference scores divided by the standard deviation of the difference scores, and if I do that, I'm going to get an effect size of 0.68. Now this is a good example of some of the concerns we have with that metric of effect, because our effect size that we get using the standard deviation of the difference scores of 0.68, that's noticeably higher, larger than our previous estimates of 0.46 for glasses delta or 0.46 for D average, right? So this is one of these cases where you could clearly see that we have more variability occurring at time 1 and time 2 as compared to variability in the difference scores, right? And so what you would want to ask yourself is, can I stand by, can I justify calculating my effect size using the standard deviation of the difference scores as opposed to a glasses delta or a D average or things along those lines, okay? But once you go through, calculate that, tell me why you calculated, why you chose what you wanted to choose, or provide a justification for the effect size that you selected. We're going to be good to go from there. So hopefully this gets you up to speed with a process of calculating paired t-tests and screening in SPSS. Let me know if you have any questions. Otherwise, good luck with the set and enjoy the rest of your weekend. All right, we'll see you.